Hello, everyone. I'd like to welcome you again to the ALCF Hands-on Workshop. My name is Brian Homerding. I'm a performance engineer here at the ALCF. So I work with the acceptance testing that we put the systems through before we put them into production. Those are many week tests that are very rigorous to make sure that the systems are ready to do productive science. Additionally, I work with the Raja team, that's a portability layer. I work on the development of the backend for the Aurora system. And alongside that, I work with the applications that are here at ALCF that are using Raja and getting them ready for the upcoming systems. In this talk, I'm going to provide you with an overview of the hardware and software going from Polaris, which is the system you have access to today, to Aurora, our forthcoming X-scale system, specifically kind of calling out some of the places where there's some differences that you're going to want to keep in mind as you develop on Polaris, so you can kind of have a natural transition when moving to the bigger systems. First, I'd like to mention a few of the other ALCF systems here. So we mentioned Aurora, that's a heterogeneous machine with CPUs and GPUs that's upcoming. There's Polaris, that's 560 nodes. That's the system you have access to today. It's in the top 500 with Rmax at 25.82 petaflops per second. There's the ALCF AI testbed, which you're going to hear more about tomorrow, I believe. And that has a variety of AI accelerators, including some that are available for allocation requests, like Cerebus and Samba Nova, and then some that are still access forthcoming, like Banagati. There's two other systems I'd like to mention briefly. There's Theta GPU. This is our kind of GPU accelerated computing pathfinder system. It has 42 nodes on it. It's kind of similar to Polaris in that it's running AMD CPUs with NVIDIA GPUs. And the Theta CPU, which is continuing a little bit longer. It's an entirely CPU machine with running Intel KNL processors. That came in at the top 500 with 6.9 petaflops per second. I also like to point you to the ALCF Support Center. While you're here at the workshop, there's a lot of staff everywhere around. I know there's a table over here, but I see them kind of interspersed throughout. And you can ask questions on Slack, but outside of that, there's the website, which has our support center, which is going to go through all the information you need to find anything about the systems or how to use the systems. It's a good resource to keep in mind. And just for a little redundancy, I wanted to recall here how to kind of get going on the machines. So connecting, you're just SSHing with your user name and to which systems you're using. So here it'll be at polaris.alcf.alnl.gov. There's workshop materials. There's a GitHub. I'm sure you all have information on this already. That's going to be useful for some of the hands-on. Our Slack space where you can see the announcements and any questions. And then there's the project. This is what you're going to be using for running on the machine. It's the fall Workshop 23, and there's two queues, as were mentioned earlier, one for single node jobs and one for scaling up to 128 nodes. There's also a project storage location in Eagle, which I'll talk a little bit more about later, in Lust Eagle projects at the fall Workshop 23. So first I'm going to walk through Polaris, covering the hardware and the software and everything you kind of need to know to be able to effectively make use of the machine. We're going to start with the hardware, and I'm going to take a bottom-up approach. By that I mean I'm going to start with a single compute node. So on Polaris, a single compute node includes one AMD EPYC CPU. This is a Milan. And there's 4 NVIDIA A100 GPUs. The GPUs have all-to-all connectivity. And there's a total of 160 gigabytes of HBM2 memory on a compute node for each node. That HBM is going to give you very high memory bandwidth at 1.6 terabytes per second. Additionally, there's a lot more memory in the DDR on the CPU for 512 gigabytes. You can get about a little over 200 gigabytes per second with that for the memory-hungry applications. Each compute node has 2 non-volatile memory SSDs with a total capacity of 3.2 terabytes. Each of the nodes gets connected out to the system through 2 Cassini NIC endpoints. And all the PCI interconnects, which going from the CPU, have 64 gigabytes per second. And the NVLink, which is the all-to-all connectivity for the GPUs, you can get up to 600 gigabytes per second. So to give you a little more information on the exact CPUs, these are what you're going to land on when you go onto a compute node. You have a base frequency of 2.8 gigahertz, and it can boost up to 3.7. There's 32 cores, each of which is running 2 hardware threads, so you'll be able to see 64 logical CPUs. The CPU is where the DDR4 memory lives. That's 512 gigabytes. It's accessed through 8 memory channels to get over 200 gigabytes per second. The CPU has a total shared cache L3 for 256 megabytes, and each core has a private L1 and L2 with 512 kilobytes and 32 kilobytes respectively. As I mentioned earlier, the PCIe connections going out from the CPU are going to give you about 64 gigabytes per second of performance. As I'm sure you noticed already, you have much bigger memory bandwidth available on the GPU and much more floating point performance on the GPU. So really you're going to want to make use of them to get the performance out of the machine. So here on the middle column is a single A100 GPU, and then HGX, that's this kind of name for this 4 GPU system. That's the entire 4 GPUs that are all connected. So on a single GPU, you get 9.7 teraflops of floating point performance. Now, if you're able to use the tensor cores on the GPUs, that's going to jump up to 19.5. And then you're able to really scale this up if you happen to be able to use some lower precision calculations. So if you go down to a floating point 16 using the tensor cores, you can get up to 312 teraflops per GPU. So a single compute node on Polaris can get you 1.3 petaflops of performance. So I mentioned the better memory bandwidth performance on the GPUs. That's because this is where the HBM memory lives. So there's 40 gigabytes on each of these GPUs, giving you your 160 gigabytes of total HBM2. So each of these has 1.6 terabytes per second. So the whole node itself is going to give you 6.4 terabytes per second. And as I mentioned before, that NVLink, if you're communicating between the GPUs, you're going to be able to pull up to 600 gigabytes per second. Really do a lot better than you're able to do elsewhere. To provide you some additional information on the node local storage, so I mentioned there's 2 non-volatile memory SSDs. Each of them has 1.6 storage available, so you have 3.2 terabytes available on each compute node. So if you're familiar with data, you're going to find it similar because we provide no specific software for utilizing the SSDs. Rather, they're user-accessible mounted volumes that you can access. You're able to kind of access them through standard POSIX APIs. Well, you get very good performance out of these. One thing to keep in mind is that the data on these are destroyed at the end of your job. So anything you want to keep out of it, you need to make sure to copy it out to either the Grand or Eagle file systems, which I'm going to talk about in a couple of slides. So now zooming out to the entire Polaris system. So as you probably heard me say earlier, there's 560 compute nodes available. Your queue that you're running today, you can submit scaling jobs up to 128 nodes. So those 560 nodes are divided across 40 compute racks on 280 chassis. As I talked about, each one of these has 160 gigabytes for the HBM bandwidth. So altogether, you're looking at 87.5 terabytes of HBM memory bandwidth. This is if you have those memory-hungry applications where you want to use up all the memory available. So the DDR on the CPUs, if you use the whole system, is going to be up to 280 terabytes. And throughout all the SSDs on all the compute nodes, you get out to 1.75 petabytes. So the network, which I'm going to be talking about next, is using HP Slingshot technology. So there's 1,120 endpoints. These are Cassini NICs using 80 Rosetta switches. This gives you kind of for the whole system a total injection bandwidth with the Cassini NICs of 28 terabytes per second. So altogether, if you look at the kind of theoretical performance for the CPU nodes or using the GPUs, if you get the TensorFloors working, you get 44 petaflops for the Polaris system with the 560 nodes. So if you're not familiar with Slingshot, I'm going to provide a little overview on the configuration here. So Slingshot is essentially how we have connectivity between all the nodes. There's 11 total Dragonfly groups. 10 of those are for the compute groups, and there's 1 non-compute service group. Between each of the groups, there's 2 links. That's providing your L2 connectivity here, where you see 2 times 200 gigabytes or gigabits. And then within a group, between all the switches of a group, there are 4 links between each of the switches, and 1 link from each of the NICs going out to the Rosetta switch. So that's 100 gigabits with Slingshot 10 and 200 gigabits with Slingshot 11. So to give you a little more detail on some of these hardware pieces, so the Rosetta switch, this offers you some multiple quality of service levels, aggressive adaptive routing, advanced congestion control, all of which together gets you some very low average and tail latency. You have high performance multicast and reductions available. So right now on Polaris, you're going to be running with Slingshot 10. That's using the HPE Cray MPI stack and Ethernet functionality with RDMA offload. And when we get uploaded, which I'm going to talk about in the next slide, Slingshot 11 is going to introduce MPI hardware tag matching, MPI progress engine, one-sided operations, collectives, and the big one which doubles the injection bandwidth. So you have to look at the top right, you'll see that your injection bandwidth is going to go from around 14 terabytes per second to 28 terabytes per second. So if you're a user here, you probably saw a notification about this, and you can see this in the support center and the facility updates. The Slingshot upgrade is coming very soon. You don't need to worry about it for the workshop here today, but it's something to keep in mind if you're going to be using the system going forward. It's going to be a phased rollout starting on October 16th, where 30% of the system is going to be upgraded. This will be in the standard maintenance windows. And then October 30th, we'll get you 60%, and then November 13th, we'll have the whole system. The one kind of main thing to keep in mind if you're going to be using the system during that time is that it will impact the maximum job size available because you need to submit either to Slingshot 10 or Slingshot 11. You can't kind of grab nodes from both. So you can find more information about that through the support center and the facility updates. Finally, I want to talk about the storage available on the Polaris system. So I kind of mentioned some of these file systems before, but now I'm going to give you some more details. So it's connected to the existing ALCF storage resources. So if you are using some of the other systems and it's your first time using Polaris, it's going to look pretty similar to you. So there's GRAN. This is our global center-wide file system. That's where our main project storage ends up going. So there's 100 petabytes, giving you 650 gigabytes per second. The access via the Lustre LNet routers on Polaris. And similarly, we have the Eagle file system, but this is our community file system, which is set up to provide external sharing via Globus. So in Eagle is also where the project space is for this workshop, which is a Lustre Eagle Projects Fall Workshop, WS. Altogether, those gateway nodes on Polaris can give you over 1 terabyte per second. And then finally, where you land when you log into the system, which hopefully everybody's been able to so far, is in your home, which is a shared file system for all the ALCF systems. It's provided for convenience, though you should not be using it if you want to use it for performance or bulk storage. Okay, so now that you kind of have an understanding of the Polaris system and the hardware on it, I'm going to talk you through all the software you need to be familiar with to be able to effectively utilize the system. And I'm going to circle right back to that file system. So as I mentioned, there's a shared home file system, and then you also have access to the Eagle and Grand file systems. They're available. They're mounted on Lust Grand/Eagle. There's also a symlink where you can just go to /Eagle/Grand. As I mentioned, main project storage is going to be on Grand, with the community project storage going on to Eagle. So kind of one of the most important things, if you're going to want to use it to build your applications, run your applications, is the programming environment. So how you're going to actually program on this system. So the programming environment on Polaris is provided through the HPE Cray APE. This provides support for HPE Cray MPI with a PGI offload to A100, so you get multi-NIC and multi-GPU support. This will support with the full Rome and Milan support. We currently have Milan CPUs, but with the NVIDIA SDK that's currently involved, I think there's a little bit of Rome support going. So for your actual programming, the kind of baseline underlying compiler support, your support for your programming models, a lot of it's going to be coming out of the NVIDIA HPC SDK. That's how you're going to be programming the GPUs primarily. It's not the only solution. For example, there's the SYCL DPC++, which we have provided also on Polaris through the Compute CPP compiler, or the Intel branch of LLVM, which offers support for offloading to NVIDIA GPUs using SYCL. So on the system, you're going to control your programming environment with the use of modules. So if you look at the top here, the module list, this is going to show you what modules are currently loaded in your environment. And as you can see here, the default is your programming environment -NVHPC. So if you need to modify this or if you want to change it, you're going to use it through the module system. You can look at module avail to see everything that's available. So you can use that to change your programming environment, but it's also where you'll be able to load various tools and libraries that are all available for your use on the system. You're going to hear a lot about those in the next couple of days. So when you actually get in for programming it, you need to kind of use some programming models to exploit that parallelism. So yeah, I kind of talked about it a little bit, but we have a MPI plus X model that's referring to using MPI to distribute and decompose your problem across the nodes or across ranks. And then you're generally going to use a different programming model to get access to the GPUs. On Polaris, we support the following programming languages, programming models with OpenMP, with or without target. So that's with target, that's meaning offloading to the GPU. OpenACC and CUDA, so those are all available and able to be used if you're running Fortran code or C or C++. Now, if you're in C, you have a couple other options where you can go to the dpc++/SYCL, or you can use HIP. And finally, there's a couple of ECP-provided programming models. This is Cocos and Raja. These are portability layers that kind of sit on top of the other vendor-specific programming models. So when compiling your code, the Cray programming environment, one of the main things it's going to provide you are a couple of compiler wrappers that are going to give you everything you need to compile your MPI application. So there's little CC, big CC, and FTN. FTN, that's your C, C++, and Fortran compilers. So these wrappers are going to include, they're going to add all the include files that you need and all the libraries you need to be able to run with MPI, and these are going to be the Polaris-specific optimized MPI implementation. Now, hopefully that works great for you, but if not, and you need to kind of understand, or you just want to understand what's happening underneath in these compiler wrappers, there's a couple of kind of important options that you can use that I find very useful. So there's CrayP verbose. So this is going to print out kind of the underlying call that the wrapper is going to use, so you can see exactly what it ends up doing. Additionally, there's these Cray print ops, so you can print out the libraries or the include flags, and these are very useful for putting into your build scripts, so you can kind of capture those and use them directly. As you can see here, you can capture the Cray libs or C flags, so this is, you can integrate it with your build script and do your separate compilation and linking. So as I mentioned, the majority of the support comes through the programming environment NVHPC with the NVHPC toolkit, but there is additional support, especially for some of the other programming models. Now GNU, this has a programming environment also, and it's kind of useful if you want to swap it. So instead of CC going to NVC or big CC going to NVC++, you can swap for the programming environment GNU, and then you're going to have GCC and G++. This can be useful for mixing with the NVHPC compilers, and this might be kind of a compilation setup that you're more used to if you're used to using like NVCC along with GCC. Additionally, there's the open source LLVM compiler. This is the upstream available for everyone to use compiler, which has built-in support for CUDA and OpenMP offload. So you're getting kind of multiple compilers to add support for your various programming models. Additionally, there's the Cray compiling environment, and the One API toolkit is installed. I'll talk a good bit more about that in the Aurora section, but essentially this is the Intel One API compiler using CodePlay plugins so that it's able to run on the NVIDIA GPUs. So you can run your SYCL or DPC++ code on the NVIDIA GPUs on Polaris. So hopefully you're all able to compile, or you're ready to compile your code, so you need to be able to interact with the scheduler. This is how you get access to those compute nodes after you are ready to go. Scheduler available on Polaris and also for Aurora is going to be PBS Professional. So there's a lot of documentation available on the web about this. There's a few commands that you're likely to have to use, especially the first two. So qsub, that's for qsubmit. This is how you submit a job to the system saying, please give me these resources and run this script on it. There's a lot of options. I'll cover some of them in the next slide, but the main thing is you need to set an allocation, which for us all here, you can use the fall workshop. There's queue stat. This is when your job is sitting in the queue if you want to see if it's started running yet or what's the current status of it. Additionally, you can pass -F or -X in case you want to get more complete information or you want to look at a job that's already finished. You can also pass -big queue. This will give you the list of queues available. So there's the 2 for the workshop that you really only need, but if you kind of didn't write down the exact wording of them or you can't find the email, you can check it through here, and it's fall workshop single and fall workshop scaling. Lastly, there's queue alter and queue dill for queue delete. This is if you need to update your request as it's sitting in the queue, or if you want to remove a job that you submitted because you decided you need to change the things. Okay, so actually making a resource request, you're going to need to pass several options. Some of these are job-wide options. So every job, you're going to have to specify a wall time with how much time you're expecting it to need. You want to make sure you have enough. So you'll pass that through the -L wall time. Then you need to do some sort of resource selection. So you can do some pretty complicated things with this, but you can also keep it kind of simple. So the second line is a -L select 128. That's saying give me 128 nodes on Polaris. Now, the system does understand that it is Polaris, so you don't necessarily need to pass the system equals Polaris, but I like to be verbose with my scripts. So if you decide you want to specify some kind of more detailed resource allocation, there's a few kind of useful definitions that are used in PBS that I just want to familiarize you with. So chunk, this is a set of resources allocated as a unit to a job. There's vnode, that's an abstract object representing a usable part of the execution host. And CPUs, that's your number of CPUs. So that's equal to your hardware threads, which if you remember, there's 64 available on the CPUs for Polaris. And GPUs, this is generally going to be 4, though if you happen to be using the multi-instance GPU mode or MIG mode, this could be higher. So just a few things with using the systems here. You kind of heard me talking about some of these already, but there's essentially a couple production queues. So you have queues specific for this workshop, but outside of that, there's a debug queue and a production queue. Here's the workshop reservations, again, just for redundancy. Also, projects are going to have an approved amount of disk space in an allocation. So if you have kind of a different project or you win an application on the system, you'll be able to check out your quotas through My Project Quotas. This is going to tell you how much disk space your project is using, what you have available. Another thing is SBank, which is going to give you information about your allocations that you have access to, how many node hours you used, how many are available. So now that we've submitted the job to the nodes, we're on the compute nodes and we're ready to execute our application, we need to run the MPI application. So you're going to land directly on a compute node, and from there you're going to want to execute an MPI exec command, which is going to use the parallel application launch service to fire off your job. So you might hear this referred to as PALs throughout the day. So MPI exec is a pretty powerful command. You're going to put in front of your actual executable. That's how you're going to launch off to your many nodes or your many ranks. So you can look at the man page for this. There's a lot of options available. I'm just going to walk through some of the ones that you're very likely to need to use. So -N, that's going to be your total number of MPI ranks or how you want to decompose your problem. PPN, which is how many ranks to put on each node. So for Polaris, a common way to do this would be to do 4 processes per node, so you end up targeting 1 per GPU. Additionally, you're going to want to control your CPU binding. So you can do this in a variety of ways. One of the ways is to set it with depth and say the depth being how many CPUs are available per rank. And then a few useful options is env, where if you want to pass an environment variable that's seen by all the nodes and all the ranks. And then there's this host file, which kind of let you specify the host file. It should pick this up automatically, which just picks up the PBS_host file environment variable. So outside of the actual launching command, there's some other ways to kind of control the behavior of the MPI layer. So is through environment variables. You can kind of do a lot of research on these, but here's 4 that I just want to call out really quickly to kind of show you what's available. So there's this GPU support enabled. So you just want to make sure that this is on. So this allows you to use MPI operations when the communication buffer is resident on the GPU attached memory. And then there's these MPH-OFI NIC options. So verbose, this is going to print out verbose information about the NIC selection. This is because when you're communicating through the network, you want to make sure you're using both your NICs to inject into the bandwidth or inject into the network. So this can help you understand how you ended up kind of breaking apart your work. And if it's not what you want, there's a couple ways to control this. So there's a policy where you can set like block or round robin, set it to the GPUs or NUMA domains, or you can do an explicit mapping with the NIC mapping. So on the Getting Started GitHub, this is a different GitHub that LCF provides. There's a very good example provided by my colleagues that kind of allows you to kind of check your affinity and understand it a little bit better. I'm going to use it as an example for a job script and also to see what you kind of end up running when you actually run with the affinity. So you can see here, the job script is going to start off with a bunch of PBS options. So here we're saying, give me one node on Polaris, scatter the one node, which doesn't do very much. The wall time, we're asking for 30 minutes. I'm going to submit to the debug queue, and I need to always set allocations so we know kind of what to build the hours to. Lastly, I need to say what file systems I'm going to be using. So I'm using Home, Grand, Eagle. You might not need all of these, but these are the main ones available. Then we get to the script that's actually going to be executing on the compute nodes. So I'm going to go into my working directory. I'm going to use this PBS node file environment variable to figure out how many nodes I have. So my script is general. And I want to run 16 MPA ranks per node. So I end up calculating out. So here we're going to be running one node with 16 ranks on it. And then we're going to use depth of 4 so that we're spacing out. So each rank has 4 CPUs, even though it's only using one thread. So an example of submitting this, but here I'm going to overwrite some of the options set in the script. So now I'm asking for 2 nodes instead of 1 and only 10 minutes. I also specify my project. So if you remember the script, I'm going to print out what we're doing. We're doing 2 nodes with 32 total ranks, doing 16 ranks per node and 1 thread per rank. And what's going to get printed is these affinity messages where it's going to print out what node they're on, what the rank number is, and which cores they're using. So you see that we start on the first node. Rank 0 is going to take the first 4 CPUs. Then rank 1 is going to use the next 4. This is going to continue all the way to rank 15, which will lose the last 4 CPUs on the first node. Then you're going to see the jump to the B1 instead of B0, and we're going to start over again. So you might walk through this example later in the day, but also it's something good to look at. There's a lot of good examples in this repo. So hopefully you're able to run, you have great affinity, everything's set up well, you get good performance and you get correct results, but just in case, we provide various debuggers in case there's bug in your code. So on Polaris, you have access to STAT. This is a stack trace analysis tool. So that provides for stack tracing at scale. There's GDB for HPC, that's a parallelized version of GDB. CUDA GDB, this is NVIDIA's GDB. It's very good at understanding on the GPU, but also just generally useful as a GDB tool. And there's the baseline GDB. And if you want to understand your performance or try to figure out how close you're getting to kind of the maximums, there's a lot of profilers and performance tools available on the system. You're going to hear more about them tomorrow during a series of talks, but I'm just going to introduce them here. So there's CRAPAT, that's a performance analysis tool, which does whole program performance analysis. NVIDIA Insight, which you might be familiar with, that's NVIDIA's system-wide performance analysis tool. TAO, the tuning analysis utilities, that's portable profiling and tracing toolkit. THAPI, which is developed here at LCF. It's a tracing heterogeneous APIs. It's tracing infrastructure for heterogeneous computing, which the systems I'm talking to you about today are. And HPC Toolkit, which provides an integrated set of tools for measurement and analysis of performance. Okay, so now that we covered kind of everything you might need to be able to use and the system, so you have some understanding of it, I'm going to go on to Aurora and again go through the hardware and the software on it, but really just drawing a focus on the things that are going to be different and you're going to want to keep in your mind as you develop on Polaris because they're going to need to be modified when you move over to Aurora. So first, look at the hardware. So I'm starting with the compute node again. As you can see here, there's a bit more going on. So there's 6 Intel Data Center GPU Max Series, again with the all-to-all connectivity. And there's 2 4th generation Xeon Max Series CPUs that have HBM memory and DDR memory. There's a unified memory architecture across the CPUs and GPUs, and now there's 8 fabric slingshot fabric endpoints. So kind of the things to keep in mind here, if you remember back to the Polaris hardware segment, now we're going from one AMD EPYC CPU to two Intel 4th generation Xeon Max series CPUs. The GPUs are going to go from 4 NVIDIA A100s up to 6 Intel Data Center GPU Max series, and our slingshot fabric endpoints are going to go from 2 NICs up to 8 NICs. So these are things you're going to want to kind of keep in your mind as you determine how to decompose your problem and set up your affinity, which is something you're going to be doing on Polaris, but then you're going to need to adjust it for Aurora. So a little bit about these Data Center GPU Max series, which you might not be familiar with. Intel provided an introduction at Intel Architecture Day a couple of years ago. You can find more and more information available online on them. It was also presented at Hot Chips. So the overall system on a chip, which includes your compute tie and your base tile and your HBM tile, everything, that's over 1 billion transistors. The execution progress is going to get you over 45 teraflops of FP32 throughput and over 5 terabytes per second of memory fabric bandwidth. So kind of to understand it a little bit better, I'm going to go down to the core. So the compute building block is the XE core. That's kind of the bottom piece. And that's going to have 8 vector engines, 8 matrix engines, giving you 512 bytes per clock. There's a L1 cache and shared local memory available. And these get pieced together. So that's 16 of them can get put together. That's going to be your slice. And then for the slice, you can go up to 4 slices, and they call that a stack. Now, zooming out to the Aurora system and what the information available today is. So the Aurora system is going to give you over 2 exaflops of double precision performance. As I mentioned, we're using Intel GPUs and CPUs. It's an HPE Cray X platform. So there's node performance is going to be over 130 teraflops, and the total system size is going to be over 10,000 nodes, as Mike mentioned earlier. Altogether, the aggregate system memory is going to be over 10 petabytes. And it's going to be using the HP Slingshot 11, which is going to be updated onto Polaris very soon. Again, using the Dragonfly topology with adaptive routing. One of the other differences is on Aurora, the primary storage system for Aurora is going to be DAOS. That's a distributed asynchronous object store. So this offers you high performance in bandwidth and I/O operations. It gives you 230 petabytes of capacity and over 25 terabits per second. So the reason I use this, it provides a flexible storage API, which will enable some new I/O paradigms, but it also provides compatibility with existing I/O models, such as POSIX MPI/IO or HDF5, if you're using those. This is an open source storage solution, so you're able to find more about it and kind of look at it online. Okay, next I want to move on to the software on Aurora, just kind of focusing in on the parts that are different and you're going to want to keep an eye out for. So a lot of the kind of like job submission and scheduling is going to look very similar, but the programming models are changing slightly. So on Aurora, our applications can use DPC++/SYCL, OpenMP with or without offload, Cocos, Raja, and OpenCL. Additionally, there's experimental support for HIP, which is running several applications already. But maybe kind of more important to keep in mind when moving from Polaris to Aurora is not necessarily what's available, but what's not available, which is CUDA and OpenACC. So if you're running CUDA or OpenACC application, there will need to be some kind of porting that you need to do. Obviously, you can kind of go wherever you want, but some kind of natural directions. So for OpenACC, you probably want to go over to OpenMP just because they're both pragma-based directive programming models. There's actually an open source project, Plaque, that tries to do this automatically for you. And if you're on CUDA, you can go to DPC++/SYCL or Cocos or Raja, or even OpenMP if you want. Intel does provide a DPC++ compatibility tool, which gives you assisted migration from CUDA to DPC++. So that means it tries to do things automatically, and when it's unable to, it kind of gives you some information to help you do it. So on Polaris, as I mentioned, the main support is going to be through the NVIDIA HPC toolkit. So on Aurora, the main support is going to come through the One API toolkit. So what One API is, if you're not familiar, it's an industry specification from Intel. So the specification provides languages and libraries to target programming across diverse architectures. So this includes DPC++, but also some low-level interfacing and APIs. So alongside the specification, Intel provides various OneAPI products and toolkits, which you're going to hear more about. But this is where you get your support for your base languages, Fortran, C++, and C, using OpenMP5 for our device offloading, DPC++, and Python. There's also all the expected libraries that you're going to get with like OneAPI, MKL, and DNN, and DAL, along with the Intel tools. So just to quickly kind of touch on these before we get into them in more detail this afternoon, DPC++ and SYCL. So I kind of keep saying both together. I'm going to explain kind of the delta between them right now. So SYCL is a standard developed by Kronos, announced in 2014. Its latest specification, SYCL 2020, was released in 2021. It's been getting revisions pretty steadily since then. It's a C++-based extraction layer that uses C++ 17 features. And it kind of pulls from ideas in OpenCL, but it's single source, meaning you can write your kernel and your host code all in one file, so it's much easier to maintain and understand. It's designed to be kind of close to the C++ standard. Now, DPC++ is Intel's implementation of their OneAPI specification, which is also their implementation of SYCL, but it includes several extensions which provide these new innovative features, so they can kind of add more around it. That's why you see that it's kind of a superset. So this is open source. It's available on GitHub. You can pull it down. If you happen to have a like integrated Intel GPU in your laptop, you'd be able to run on that using SYCL, but also you can use the NVIDIA backends because there's a plugin interface which allows DPC++ to kind of target these different things, and that's what's working on Polaris. So there's OpenMP, which you're likely familiar with as it's a very widely supported and utilized programming model. If you're not kind of familiar what's up to date with OpenMP, OpenMP5 added constructs for directed-based programming to GPUs. So this is available for both systems for C, C++, and Fortran. The current spec provides the support for running on the GPUs. It was added a little bit ago, but now it's really getting integrated. Because of this, it provides you with one option for having performance portability. This is because you have multiple compilers and multiple vendors that are supporting it. And just to kind of quickly mention that there is some community consensus about what are the most important features. That being, if you kind of start coding with it and want to switch and you're using a different compiler, the same features should be supported because as you probably realize, it's not likely that every compiler is going to support the entire spec all the time. So there's some things that don't make sense for the GPU that won't be supported for the GPU implementations. So for Aurora, there's Intel Fortran, so this is going to be offering support for Fortran 2008 and OpenMP5. It's a new compiler that's built on top of LLVM, but it's utilizing Intel's strong history of optimizing Fortran compilers. You can download the beta today in the OneAPI toolkits, so you can try that locally to see if you're able to compile. As I mentioned, you're going to have access to all of the libraries that you come to expect, such as MKL, which is going to give you your math kernels for FFT, BLAS, LAPACK, sparse linear algebra, so on. This is optimized for every Intel platform, so that's going to give you an optimized version for both the CPUs and the GPUs. You can read more about it online with the OneAPI MKL, which gets abbreviated for OneMKL. So the additional tools that you're going to get outside of kind of more general community tools, which will be available, you have Intel's tools of vTune Advisor. So vTune is a profiler. It's a pretty widely used performance analysis tool, and it does have support already for Intel GPUs. There's Advisor, which you can use to pull down a roofline, which is a very nice abstraction for understanding how well you're using the underlying hardware. But it also provides offload analysis, which identifies potentially profitable locations if you're porting your code to the GPU. So it's essentially going to run your code kind of as it is on the CPU. It's going to understand what's going on, how much time and behavior is happening. It's going to model the architecture that you're trying to port it to, like the GPU, and then it's going to consider any data transfer or kernel launch overheads, and then try to give you some advice as to, I think this loop or this section is going to run pretty well on the GPU. You should offload it and you'll get some performance gains. Okay, with that, I think we covered the main things that are going to be kind of the delta going forward. Hopefully you all have some understanding of the system you're going to be using today and the software that you're going to need to utilize to use it. And with that, I'll just leave you with a couple of pointers. So as I mentioned earlier, there's the support center. Obviously, while you're here at the workshop, you can come talk to me or any of the other staff here. There's a lot of experts available for you to interact with, and we hope you do. Also, there's the Slack where you can ask questions. You can go into the breakout rooms, ask questions there, and we'll get you your answers. But there's also a lot more information on the systems, including some of the other and upcoming systems on our ALCF website. So here's a link for Polaris. And finally, if it's after the workshop, if you're having any issues, you can always email support@alcf.anl.gov. Okay, thank you.
Thank you, Brian. Are there any questions? Yes.
So you say Aurora is going to be to petaflop, to exaflop. So so before you set up a machine, how do you know how it's going to perform before you have a chance to test it?
So that's sorry if I didn't say it, but that's a theoretical peak performance. It's essentially what it's designed for if you look at it, yeah. So it's not a measured one, it's just what's expected to be available.
Any more questions? We're actually early for this talk, so we have time for plenty of questions.
You have the metric for, or I mean, estimation for the single precision in Aurora, theoretical peak.
For what?
For the single precision.
Single precision on Polaris?
Aurora.
Not off the top of my head that I'd be able to remember. I can follow up with you on that.
Is there any documentation or a single document that I could go to assess the qualities of every particular machine in your fleet?
So if you go into the support center, basically it's kind of divided with documentation by system and then by kind of subject. But if you click on each system, it's going to kind of be broken down in the same way. So you can't really get them all side by side exactly, but you're going to find it very familiar if you look at the documentation through Polaris, where you can kind of like look at linking and submitting jobs and everything. And then if you go on to the documentation for the other systems, it's going to be broken down in a very similar way.
Yeah, I can paste a link to documentation for Polaris and other systems that is available on this slide. Just notice that only like 30 people in the slides channel and other Q&A. Make sure you join it, because all the questions and everything that is happening there, you won't see it if you don't join it. You just have to click join from the announcement. Everyone is in the announcement. Are there more questions?
So I have a question related to the math kernel library. And so the Intel vTune and Advisor is only used for the Aurora, or is it for the Polaris and Theta too?
So it's definitely available on Theta. I don't believe it's available on Polaris as it's underlying CUDA control. But you have NVIDIA's suite of toolkits. I didn't kind of go into the details on them. I think there's talk about it tomorrow that's going to give you some more information, where it's a pretty kind of similar interface where you're able to go kernel level performance, understand all your metrics and kind of how it fits into the overall architecture.
Thank you.
You have shown that Intel DPC++ compatibility tool is existed for CUDA to CCAL migration. Is it a cyclomatic tool or any other tool? So Intel has a tool called cyclomatic to convert CUDA code to CCAL code. So does Aurora support cyclomatic or any other custom tools?
So the compatibility tool, yeah, if you run it with cyclomatic, it should it'll be supported because you just need to get to the sickle code underneathing. We might be referring to the same code. I might be not up to date with the naming for it.
Thank you.
I have one question about the Polaris topology. I found that you split the whole cluster into 10 Dragonfly group. So the node end-to-end, like the point-to-point bandwidth across the group and within the group is different, right?
Yes. Yeah, that's why I kind of covered some of the kind of more detailed resource selection you can do when you're submitting a job. So you can try to get nodes that are more together in a group to try to get better bandwidth.
Okay, thank you.
Any more?
For the upcoming Slingshot update, could you comment on how the user will be affected by the injection bandwidth, and for which workflows would be more affected by this upgrade?
For the Slingshot upgrade?
Yeah.
So there's additional information on the web page. You might end up needing to recompile your code, but essentially if you're kind of bound on your injection bandwidth, you're going to see some nice improvements for it, is the expectation.
I just realized that we are underutilizing the Polaris, especially for the SSD space. So how we access to the local disk?
Yeah. So as I mentioned, it's just mounted under I think it's /x SoC. Just basically, it's mounted as like a regular file system on there. There's no kind of special software available. You can kind of use it through standard POSIX APIs for moving your data.
One single folder gives me access to both.
I want to say it's 2, but I haven't used it recently, so I'm not certain on it. Yeah. If you get an interactive node and just check on like DF or DF, it should show you kind of which ones and where they're mounted.
I'm wondering, is there any strategies for use of Polaris in particular, especially with the new Slingshot coming in? Is it actually better to pull things over the network than it would be sitting on the hard drive?
So for
processing to pull data down rather than having it sit on the hard drive and pull from there. Just,
so basically, sorry if I didn't hear part of it, but to utilize the Slingshot kind of effectively, that's why I kind of went through on the affinity control. So you want to make sure to use you have good NIC mapping so that you're kind of using both your NICs for your interface out to the network. And then as far as the actual performance on the network, as we mentioned, it can depend on kind of where your nodes end up landing and which links you end up using. So it's kind of a very difficult problem and something you need to keep in mind.
Brian, are there any particular areas of research you're excited about for Aurora?
Particular areas of research? There's many. There's a lot of really good results that have been shared publicly through like ISC recently. I didn't cover them here, but there's a lot of projects that we're working with that are getting ready and going to be ready to use science on day 1 for Aurora. So there's a lot of really interesting problems that are going to be available to be used. I work with the EQ Sim team that's earthquake simulation code. So basically this is doing propagation kernels throughout. So I'm pretty excited to be running on that. But yeah, there's a lot of good science that's upcoming, and you look at the problems they're trying to solve, and it's really interesting work.
Thank you.
What Brian said, we do have early science project that is selected applications who are working directly with us to get access to the machine. And like for their application, we also work with a lot of ECP, so exascale computing project. There is like, I don't know, 20, 30. So there is a lot of activity going on, but some of the information is still in DA and some is going public, and more every day has become public. So I think you will see a lot in the SC this year. Any more?
When and how can users who are not part of an ECP or early science project expect to get access to Aurora or maybe Sunspots, which I believe is it testbed for Aurora?
It is. I would need to follow up with you on that. I don't have that information available myself. Generally, the way you get access is through our allocation programs, which you're going to hear more about this afternoon.
We have applied for insight on Aurora, but we haven't run on it yet, obviously.
Yeah. Right. Yeah. Yeah, I don't have any specific dates to tell you at this time.
Somewhat related, you mentioned that different compilers have not necessarily implemented all the specs for, say, OpenMP offload. Are the same compilers available on Polaris, or in particular the Intel compilers, are they on Polaris? You may have mentioned it, but...
The Intel OpenMP compilers, I do not believe are available on Polaris, but there is communication that some of our team members kind of work with between like NVIDIA and Intel to make sure that they're kind of understanding the spec the same and things are getting implemented the same. So the idea being that you're not going to switch and automatically like, oh, we don't support this feature. So it should be supported. If it's supported on one, it should be supported on all. So you actually get that performance portability that you want.
Thanks.
Any more? Well, if not, let's thank the speaker again, and we will have break after that.